auto's velocity starting from rest is given, where v is measured in feet per second. To the nearest hundredth, find the vehicle's velocity and acceleration at each of the following times. All right, so they're not giving us the position of the auto, the vehicle or whatever sort it is. They're giving us the velocity model. So they're asking us first to figure out what v of 1 is, and then they want the acceleration, so v prime. All right, v would be velocity, v prime would be acceleration. All right, the derivative of velocity is acceleration. So they're asking for v prime of 1 in addition to v of 1. But then they also want it for 5 and 10. All right, so this is just number crunching. Now, if we had to compute the derivative by hand, it would be a little bit more complicated, but we don't, so it's not. All right, so if I just need to figure out v of 1, I could just type in v of 1 after I put in my function and get my result. All right, this is a contextual situation, so I want to make sure I have the appropriate units. But v of 1 is going to be about, they said nearest hundredth, so 6.43. So I could jot that down. Yep. Helps to put the 6 first. And they said feet per second. So I have that. Now I'd have to change that 1 to a 5 and then change that 5 to a 10. Or I can make it v of a and create a slider and then slide over to the 5, which would give me an even 15. All right, so 1 gave me the 6.43, 5 gives me an even 15, and then 10 gives me an 18. All right, and so if I want the acceleration, I just need v prime of a. Notation-wise, it's just what I have on paper. So v apostrophe, and then pop in an a. We already have a slider for a, so why not? All right, and then just slide my slider appropriately. Well, I already have it at 10, so I might as well just chuck that in there. That's 0.36. That's feet per second squared. All right, so feet per second. All right, so it's the rate of change of velocity per unit of time. So it's the rate of change of feet per second every second. All right, so that's where the second squared comes from. All right, but I got to get it for 5. So 5 is an even 1. And 1 is about 4.59. All right, so it's kind of weird to think about when you're looking straight by the numbers here, but we have an object that seems to be speeding up, but the rate at which it's speeding up is slowing. All right, so you can try to visualize that, but I think it's kind of, I mean, if you drive, you could probably think of an instance in which that's happened. You're gunning it from a stop sign or a stoplight. You're like peeling out, do a little fishtail, burning some rubber, flooring it, gunning it, and then you see the cop, and then you slow down. No, it's probably not that bad. But like you accelerate from rest. You're pressing the gas pedal down a little bit more early on to get up to speed, and then you ease back off of the pedal once you get up to the desired speed. All right, so the rate of increase starts to decrease. All right, so I always kind of looked at it like the velocity is the speedometer, the acceleration is how much you're pushing on the gas pedal. Right? So you're really pushing it down hard, that's a high rate of acceleration, or you're dialing it back, that's a low rate of acceleration. Right? So, or even a negative rate of acceleration if you're actually decreasing in the speed. Right? But it's a cool thing to try to visualize. It takes a little getting used to, but we'll get the robots involved before too long, and we'll see. All right. So anyway, number 4, a bolt is dropped from a bridge under construction, falling 89 meters to the valley below the bridge. Rounding each to the nearest hundredth, what is the speed when it begins that I guess, last 27% of its fall? I would think that would probably be the last 27% of its fall, but whatever. What is its speed just before it reaches the ground? All right. So we can start off with a position function. So we have an object that's being dropped. So the position function S of t, 1/2 gt squared plus VOT plus SO. Unit of change, geez. Let's see, what do we have here? 89 meters. All right, so the units of the acceleration due to gravity would be meters per second squared. So gravity would be negative 9.8 meters per second squared. And so everything is going to be in metric here. All right. So I have an object that's being dropped, and I'll just draw a very rudimentary sketch. You have the bridge. Okay, I mean, that's as good as I can get, I guess. But then you have an object that's being dropped to the valley below, and that's a total of 89 meters. All right. So we're only really concerned about, or with the speed, once it hits that 27% mark. All right, 27% off of the ground, because it's the last 27% of its fall, so it's already fallen through 73%. All right, so we got 73% of the fall, and then this would be the last 27%. All right, so just quick computation, 27%, so 0.27 times 89, so 24.03 would be the height at that moment. So 24.03 meters. That seems to be the only reason why we need the percent values, just to figure out what that height would be. All right, it's a total of 89 meters, 27% of which is what we're concerned with. All right, so that would give us the moment in time that we're concerned with. All right, an initial velocity, it said it was dropped. Okay, so if something's dropped, it's not pushed down or thrown down, so it doesn't have an initial velocity. So we would say v sub o would be equal to 0. All right, so it's not released with force, with a downward force. It's just acceleration due to gravity taking hold. All right, so we have an initial height, we have acceleration due to gravity, and we have a moment in time that we're concerned with. We just don't know what it is yet. We'll figure that out in a second. All right, so, but we'll come up with our general position function, which would be 1/2 times negative 9.8 t squared. The VOT is irrelevant, so plus 89, which gives you your negative 4.9 t squared plus 89. That's my position function in terms of t. All right, now if I differentiated this and put a value in for time, I could come up with the velocity, but I don't know what the time is yet. All right, I do know the height that it will be at the desired moment. Right, when that 27% of its, well, after 73% of its fall has been completed, and there's 27% of its fall that remains. So I can take this instead of equal to 24.03. and solve, I could do this. This is actually pretty easy to do algebraically. You know, when you're dealing with quadratics that involve decimals, it sometimes could be annoying. You got to get into the quadratic formula and all that stuff. But here it's in binomial form, so I could just subtract off the 89. You really don't need any fancy Desmos tricks here. I mean, you're welcome to use fancy Desmos tricks, of course, but the only Desmos trick I'm going to use here is simple arithmetic. So 24.03 minus 89 is negative 64.97, yep, is equal to negative 4.9 t squared. Divide both sides by the 4.9. Negative 4.9, that is. Talking like 13 and change. So t squared is equal to 13.259, etc. A bunch of other values there. But I can just take the square root of that. So I can put the whole thing in parentheses and raise it to the 1/2 power. That'll take the square root of it. Or I can do something that is a little bit Desmos tricky. I could define some variable, some value to be equal to that number, and then take the square root of that defined value separately. Either way. All right. Either way, you should come up with about 3.6. So 3.64 and change. I'll go 3 decimal places before I start the dots. I'm putting the dots because I'm still working with the full decimal value. I'm just only writing out three decimal places. All right. So that doesn't really fully answer the question. I mean, it doesn't answer the question at all, but it's the key ingredient needed to answer the question, because in part A it says what is the speed when it begins that last 27% of its fall. In the prequel to part A, we figured out the position function, right? So I'm just going to pull that. The derivative of that would give me velocity. So S prime of t is the same as v of t, so just make a little note here. V of t is equal to S prime of t. And then I would just differentiate this expression. All right, so I take the derivative of my position function, just using the power rule. 2 times negative 4.9 is negative 9.8 times t. Reduce the power by 1. Constant goes away because, again, if we're looking for a derivative, we're looking for a rate of change. If something's constant, that's a new word, constant, its rate of change is 0. Therefore, its derivative would be equal to 0. All right, so negative 9.8 times time would give me the velocity. So at the moment that it will have passed its last 27, or at the mark of 27%, we would have whatever this is when you plug in that 3.641. So V of 3.641 and so on would be approximately equal to negative 9.8 times that 3.641 and so on, which I would get just by either typing this raw decimal in, which is probably not as entertaining as it might seem, or designating this as some other variable and plugging it in that way. You know, you could let C equal this and then, multiply that by negative 9.8. You could also just take this number and multiply it by negative 9.8 directly. All right, so you get negative 35 point, they said nearest hundredth, I believe, so negative 35.68. And that's meters per second. So that's part A. Part B is just kind of like the same question again. Because it's saying, what is the velocity the moment before it hits the ground? I mean, the reason it's phrased that way is because once it hits the ground and comes to a velocity of zero, it's all the energy is transferred. It's kind of a philosophical thing, like mathematically it still has velocity, but in a practical sense, I mean, once it goes splat, it's over. There's no more velocity anymore, right? But if it's just the infinitesimal moment before it hits the ground, that's where it gets theoretical. Like, I can't even say that split second. I'd say that infinitesimal difference between the moment it hits the ground and the moment before, then we would have something more meaningful. That's where the concept of a limit comes into play. All right. So all we'd have to do here is figure out what its velocity would be at the time when it would have hit the ground. All right. So I got to figure out how long it would take to hit the ground. And there's two ways to do that, just like I was saying before with fancy Desmos stuff, or by taking my position function and setting it equal to 0 to get a value for time, which we would then plug into our derivative function. I believe I hear the dulcet tones of Mr. Cohen. So anyway, add 4.9 t squared to both sides. Divide by 4.9. And basically I'm just doing what I did before, except now I'm not putting it in Desmos right away, because you saw what happened with all that decimal stuff. Might be worth it to just leave it as a radical, all right, because it's pretty hideous no matter how you slice it. All right, so t would be equal to the square root, because we would have this 89 over 4.9. T squared would be equal to that, so I would just take the square root of both sides, and this would be my value for time. If you're interested in knowing what that is, you could just chuck it right in real quick. So it takes about 4.2 seconds to hit the ground, which is pretty consistent with what we already came up with. It took 3.6 seconds to get 73% through the trip, so okay. Another second or so to go the rest of the way. That doesn't seem unreasonable. All right. So this value, so again, approximately 4.262, is what's going to get plugged into our first derivative of negative 9.8 t. All right, so all I'm doing is replacing the t in there with that 4.262. But you could do it in the general form of having the radical there, because Desmos can handle that pretty easily. So v of, and I'll say 4.262 blah, 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 is approximately, and I'll just chuck the negative 9.8 multiplier right in front. Negative 9.8 multiplied by that value of time, which is the square root of 89 over 4.9, would give you about, again, to the nearest hundredth, negative 41.77. Say that's a spur of the moment situation where he didn't really think about what he wanted to say before he went by a classroom of 30 people. Sometimes a little planning ahead of time goes a long way. All right, so yeah, it had a little bit more speed as it contacted the valley below the bridge. So that seems to make sense, I think. All right. And the negative just indicates it's going in the downward direction because velocity is a vector quantity. If we're talking about the difference between, and in this case, a free-falling object is only going to go up or down. Positive would be in the upward direction, negative would be in the downward direction. It makes sense that both of these quantities would have negative signs. Right? There's never an instance where this bolt is going back up. So we don't want to get thrown off or dismiss anything just because it's negative. If the time was negative, which it could have been, by the way, I kind of glossed over that. Taking the square root of a number would give you a positive or a negative value. We didn't even consider the negative values because that would be moments before the bolt was dropped, and that wouldn't make any sense in this context. All right, so that was disregarded. But anyway, all of this would amount to part B of this question. And, it's substantial, but if you really think about it, and this I've said this for years, but it doesn't make anybody feel any better every time I say it. The calculus happened right here. Everything else was pre-calc and problem solving. The part that was unique to this course, the part where we took a derivative, happened in that one step. So all of this work, 99% of this work, is all unrelated to the material from this course. So the stuff that made this question hard had nothing to do with the calculus. All right. So that's not to make anybody feel bad. Like, oh, I didn't understand it, so that means I guess I got to go study physics or something. No, it's like, it's actually should go the other way, where you would say, okay, at least I have the calculus down. All right, now I just got to work to try to wrap my brain around the physical aspects associated with a question like this. All right, because if you got the negative 9.8t, if you had a thought of like, I understood everything related to the calculus part of it, it was the background and the applications of it that I'm struggling with, then we'll get you there. It's if you have the calculus down, we got something to work with. All right, so that's the important piece. All right, so that should be good news anyway.